Hello folks, welcome to CS412 Software Security. This is the speedrun of OX07 Advanced Mitigations. Let's get right into it. The learning goals for today are as follows. First, we want to understand the limitations of basic mitigations and some additional need for advanced mitigations, which we will discuss today. We will explain control flow hijacking under active mitigations and then differentiate some of the follow-up research on control flow integrity, code pointer integrity, and software-based fault isolations. We'll also discuss some limitations of the above mitigation so that you can distinguish them and figure out what the different options and possibilities are. So there's a couple of advanced mitigations against control flow hijacking that were developed in addition to the mitigations we've already seen in class before. Control flow hijacking is the attack vector that gives the attacker the highest flexibility. It allows the attacker to execute arbitrary code and therefore gives them a lot of power to do anything they want. So it's the most versatile attack vector that allows them to then just decide only later on what they want to do. The deployed mitigations we've already discussed make control flow hijacking quite a bit harder, but not impossible. So you've seen that there's still a couple of vectors out there that can be used to hijack the control flow and then go on and use it for different kind of means. So the goals for all of these advanced mitigations is to further restrict control flow hijacking through a set of advanced protections, limiting the amount of control that an attacker can get over a program, and as good as possible prohibiting arbitrary code execution and forcing the attacker to adjust their attacks on a program-by-program basis, requiring a lot more additional work and making this overall much harder. So if you look back at our model for control flow hijacking attacks and different kind of attacks, we've seen that there's a couple of different paths that the attacker can take to get to code corruption or control flow hijacking. If you look at the combined mitigations, we see that code corruption is fully mitigated and control flow hijacking is severely limited, making it much harder for the attacker, but not impossible. We see that there's a couple of restrictions on code pointers and data pointers and some additional protections against the location where the attacker will have to guess which location is the correct one or use some kind of information leaks. There's only limited checks on the usage of the pointer through, for example, the stack canary mitigations. And this is certainly an area where we'll look at further. How can we further check the use of control flow code pointers to further limit the attacker to no longer be able to hijack the control flow? If you look at requirements for control flow hijacking, the attacker must on one hand first overwrite a code pointer with a known value and then trigger the usage of the modified code pointer. Protecting the first two dimensions, like protecting the code pointer from being overwritten maliciously or from actually guessing the correct value, are very hard to achieve in practice. While we can shuffle the values a bit, protecting against the information leaks is incredibly hard, and enforcing integrity or write integrity of any kind of code pointers is similarly difficult to achieve. So memory safety is computationally too expensive, and randomization or diversity is incomplete due to the information leaks I already mentioned. Advanced mitigations therefore all protect the code pointers through usage checks, as in the last layer that we've seen in the image before. So they check the integrity whenever a code pointer is used against a certain target set. There's a couple of different targets for control flow hijacking attacks in code. Like if you look at C and C++, function returns, function pointers, virtual dispatch, and switch statements can be targeted. All of these statements have a form or result in a form of indirect control flow, which means that the target is determined at runtime, and the source code or the machine code cannot encode the actual target in the code area, which means that the target is encoded somewhere in writable memory. So this is either on the stack or on the heap. For function returns, function pointers, virtual dispatch, and switch statements, All of these targets have in common, all of these statements have in common that the target where control flow will be redirected to is actually in writable memory somewhere, and therefore also dependent on the execution of the program. If you look at defenses against control flow hijacking using the current set of mitigations, if you assume code integrity and data execution preventions, adversaries must override code pointers and redirect control flow to existing code regions, therefore reusing the code in unintended ways. Indirect jumps are not reasonable targets because switch statements are usually bound checked by the compiler if the compiler is correct, and jumps in loader data structures are write protected, as in all of these different fields. Therefore, indirect jumps are very hard to actually redirect, modulo bugs in the above two issues. Returns are a classic target, with indirect calls the alternative. So most attacks leverage indirect calls or the return instructions on the stack, depending on the rollout mitigations and protections. Due to ASLR and stack canaries, returns are harder to exploit, and some attacks have been shifting towards indirect calls for now, at least for the first gadget. So the first gadget would result in an indirect call that redirects and hijacks control flow, followed by a stack pivot, and then usually a rob chain or something like that. Switch statements, if you switch through a set of targets, are usually bound checked. We've recently published a paper on bypassing these kind of bound checks through compiler-introduced double fetches, which allow the adversary to modify the target after it has been actually read. If you're interested in more details about the attack, I refer you to the paper which is on the group's homepage. It's called Warp Attack, Bypassing Control Flow Integrity with Compiler-Introduced Double Fetches. Okay, so far so good. So what are the advanced mitigations that we want to look at today? First, stack integrity. How can we protect the return edge? So on the stack. Then control flow integrity. How can we protect indirect calls? And code pointer integrity, which also protects indirect calls, followed last by sandboxing, which restricts the targetable code. So further branching off and segmenting the code into smaller areas that can then individually be protected to, for example, create smaller target sets. The attacker model that we're going to use for all of the advanced mitigations is as follows. We assume that the attacker is extremely powerful and can mitigate or bypass probabilistic defenses. The attacker can read data and code. So all the data, stack, the zero initialized data, globals, code regions, heaps, and so on, is completely accessible to the attacker through an arbitrary read. While randomization-based defenses usually limit the attacker in some way, as they are probabilistic, there's often information leaks and other ways to get around those. So to be safe, the defense, these mitigations simply assume that the attacker can read data and code. Similarly, the defense is assumed that the attacker can write arbitrary data. So anything on the stack or on the heap is writable to the attacker. The defense is also assumed that the attacker cannot modify code, otherwise they could patch out the defenses and simply modify the code as follows. And also that the attacker cannot influence the loading process, as in the attacker cannot inject arbitrary attacker controlled code. This kind of limits or assumes that, hey, we've started in a safe state and there's no attacker controlled code in the process. This is actually an interesting limitation or assumption from these advanced mitigations, right? We are starting in a safe state, and then the mitigations continuously ensure that we remain in a safe state. Okay, so let's start with the first one, namely stack integrity. Stack integrity ensures that the return instruction pointer and the stack pointer cannot be modified by the attacker. So this mitigation protects the return instruction pointer and thereby the instruction pointer and the location of the stack, so that the stack cannot be shifted or pivoted to alternate regions. Return instruction pointers are code pointers, right? The key issue is that they are saved on the stack and thereby could potentially be modified by an attacker, as this is a well-known location. Stack integrity guarantees that the return instruction pointers cannot be modified and enforce integrity. So only valid return instruction pointers are ever referenced. Pointers to other stack frames are stored on the stack, and stack integrity ensures the integrity of this metadata as well. For example, modifying the base pointer indirectly modifies the return instruction pointer. Therefore, both of them, the stack pointers and the return instruction pointers on the stack, will have to be protected. Stack canaries are a weak form of stack integrity, as they check the integrity through an additional canary. Shadow stacks are a strong form of stack integrity, as are safe stacks, which also protect some data in addition to that. Memory safety would give us full stack integrity as a side effect of enforcing the high-level property, but usually comes at a higher cost. So let's look at shadow stacks and safe stacks in a bit more detail. Stack canaries we've already covered in previous classes. So for shadow stacks, the assumption is that a second shadow stack is allocated right next to the original stack. But on this shadow stack, we only keep the copies of the important data, as in return instruction pointers and, for example, the stack pointers. And then whenever the control flow returns to a previous function, we can check the integrity of the data on the regular stack frame with the data that we have stored on the shadow stack frame. Not all implementations protect all data, and there's different kind of alternatives in the implementation, but this is done through additional checks. Data on the shadow stack is integrity protected implicitly, as in the original data, the data on the original stack is not write protected, but a copy is going to be allocated on the shadow stack, and then this copy on the shadow stack can be checked against the data that is on the regular stack. The shadow stack is protected either explicitly, because some shadow stacks are write protected, or implicitly by just relying on address space layout randomization to allocate the shadow stack somewhere in a random area of the address space. Data corruption can be uncaught. So for example, if there's a buffer overflow, other adjacent variables on the stack may be corrupted. And there's different ways to implement the shadow stack, and varying different forms exist, also dependent on the architecture. A high-level figure of a shadow stack looks a bit as follows. We've got the stack that grows from top to bottom. We've got the return instruction pointer in the black frame, and then the new stack pointer, the return instruction pointer, and so on. And the shadow stack simply contains these data structures for instruction pointers and stack pointers for each individual stack frame. And when the function returns, the additional code will verify the integrity of the data on the existing stack with the data that is on the shadow stack, making sure that they actually match and that the return can safely continue in an obvious safe way. Now, this is the first mitigation. Shadow stacks allocate a stack frame on the shadow stack and on the original stack for each function that is being called. So every time a function is being called, a new stack frame is being created, both on the original stack and on the shadow stack. When a function returns, the check ensures that the protected data is correct and the integrity has not been violated, and then the stack frames on the shadow stack and on the stack will be deallocated. Now, the safe stack is a somewhat of an conceptual optimization of the shadow stack. A shadow stack always keeps two allocated stack frames for each function call, and the safe stack kind of changes the perspective a bit. Under the assumption, the core idea here is that many of the variables on a stack frame are only used in a safe way. And then this safe stack also protects the safe variable. So any variable that's only used in a safe context, for example, its pointer is never taken, the variable doesn't escape the current function, and is only used with very bounded pointer arithmetic. Now, the idea here is that we can allocate all safe variables on the safe stack. any unsafe variables will be allocated on the unsafe stack. So we still have two stacks, right? The safe stack and the unsafe stack. We will allocate all safe variables, including the return instruction pointer and the base pointer, on the safe stack, and all unsafe variables will allocate on the unsafe stack. Now the key advantage here is that if we can prove that all the variables are safe in a stack frame, we do not need to allocate a secondary stack frame. And this on one hand protects all the data, all the variables that has been proven safe, plus only requires allocation of a single stack frame, thereby massively reducing the overhead of the shadow stack. So there's a performance benefit and a protection benefit for safe variables. Unsafe data, corruption remains uncaught though. So if you look at this, right, if you look at an example of a safe stack and a regular stack, we've got this function foo that has a buffer that is used in an unsafe way and escapes to scanf, and a local variable r, and the return address, of course. So the safe stack will contain the safe variable r, the return address, and all the other metadata, while the regular stack will contain the potentially vulnerable buffer. Okay, cool. So far so good. So these are safe stacks and shadow stacks. So the summary for stack integrity is as follows. Stack integrity protects some stack data, at least the return instruction pointer and a stack pointer, and prohibits control flow hijacking by modifications of the return instruction pointer. Stack canaries are a weak form of stack integrity that protect against continuous buffer overflows, but not against arbitrary writes. They come at a negligible overhead. Software shadow stacks protects against control flow hijacking, but allows data corruption at medium overhead. Hardware shadow stacks, if it's implemented in hardware, again, they must massively lower the overhead. Safe stack, the key benefit here is that it protects additional safe data at very low overhead and can be used in a software-only implementation. Cool. This covers the return instruction pointers and the backward edge on the stack. Let's look at how we can protect the forward edge. The key mitigation, a key advanced mitigation in this area is control flow integrity. And control flow integrity is a mitigation that protects applications against control flow hijack attacks. The CFI mechanism will ensure that the control flow of the application never leaves the predetermined valid control flow as according to the control flow graph from the source code or at the application level. So this means that the attacker cannot redirect control flow to alternate location. So if you have a function pointer that is being dereferenced, as shown in this code example here, it is prepended, the CFI check executes a check on this function for this particular location. So it checks if the currently observed value of the function pointer is in the set of valid function pointers. So without this check, the value could point, the value that that function has in the program could point to any location in the code area. And the indirect call would happily transfer control flow to any valid location in the control in the target application. But the check will ensure that only a few locations are valid and allowed. If any of the invalid locations are being discovered at runtime, the program will be terminated. So if any but the two gray arrows are being used, or any target is observed at runtime that is not the two gray arrows, the application will be terminated. The goal of control flow integrity is to restrict the dynamic control flow of the application to the control flow graph of the application. This requires two steps. First, we need to construct the target sets based on some form of static analysis, and then enforce these set checks at runtime. How do we construct the target sets? Well, it's kind of hard, right? The control flow graph, while it is more a conceptual data structure than a data structure that actually exists. A static analysis can recover an approximation of this control flow graph. And of course, for the security aspects of control flow integrity, the precision of this analysis is crucial. Now, imprecision is also an issue because if the control flow graph is imprecise, there could be false positives where the control flow mechanism, the control flow integrity mechanism terminates the application for valid targets, and that's something that we clearly don't want. So the target set construction leverages, for example, all the valid functions. Well, we could construct one single set of all the valid functions and simply enumerate all the functions in the program. And this is a very large set. And the set check would just check, is this a valid function? This would be a valid control flow integrity implementation. But one single large set gives the attacker still the option to choose among any target in this set. Therefore, arity increases on this and defines a tighter set where it creates one set for each set of functions with the same number of arguments. So there will be one set with 0 arguments, one set with 1 argument, one set with 2 arguments, one set with 3 arguments, and so on. And the control flow location, the instrumentation will check how many arguments does the target take, and if so, compare against the corresponding set. Even more precise, we can leverage function prototypes based on the actual types that are being used, or even more class hierarchy analysis that further restricts the set of targets based on the class type hierarchy as defined by C++. Right, so there's implicit trade-offs here in the construction of target sets, namely a trade-off between precision and compatibility. One set of valid functions is highly compatible with other software, but may result in imprecision given the large amount of functions. Class hierarchy analysis results in very small sets, but may be incompatible with other source code and some programmer patterns. For example, if you're casting to void or not passing all parameters, this may be an issue, right? And this will potentially result in false positives where the control flow integrity mechanisms terminates valid programs. Now, Microsoft in their implementation chooses compatibility over security. So there's one set of all valid functions. LLVM CFI chooses security over compatibility. There's one set for each function prototype. What are the trade-offs? Well, one set is highly compatible, but gives attackers an ample choice for targets. So usually, while attacks are being harder, there's sufficient amount of targets in there to allow an attacker to actually hijack the control flow if they just spend enough time analyzing the possible valid functions, because these functions now kind of provide a set of gadgets, one function gadgets that can be used by an attacker. Sets on a per function prototype basis restrict the attacker, but may require code adjustment, which can be quite heavyweight and require additional modifications to the software. Right, so there's an interesting trade-off between security and compatibility. You can definitely start with one and then move to the more precise one. The runtime check is as follows, right? The analysis produces the target sets that we have for each location of an indirect control flow transfer. The runtime check then leverages these runtime values that are being observed from the execution of the program and the target set to execute the check. And in the end, this is kind of a set check. If the target set does not contain the function, then we abort with an error that says, hey, this is an illegal target. And only if it is allowed and in the target set, we will let the function continue. Now the compiler needs to make sure that when the target for function, the actual address of function is being loaded from memory, it stays in a register throughout the set check. So there cannot be any kind of time of check to time of use attacks against the target set, right? So this must be an atomic read of the function pointer that is used in both locations for the check and then for the second step later on. So what are the limitations? CFI allows the underlying bug to fire, so the memory corruption actually happens. The attacker can overwrite the target pointer, can modify the target pointer, and the defense, the mitigation, only detects the deviation after the fact, as in when the corrupted pointer is actually used by the program. Now the over-approximation in the static analysis reduces the security guarantees, and there's still several kind of attacks are possible. Right? For example, An attacker may modify the outcome of any JCC by, for example, modifying data values. Right? Any conditional jump can be modified by the attacker and can be redirected and adjusted to some form. An attacker can choose any allowed target at each indirect control flow location. So the attacker can choose, by controlling the target location, what different kind of targets are being reached among the set of the valid targets, right? So this gives the attacker actually ample choice. For return instructions, one set of targets is way too broad, and even localized return sets are too broad for most cases. That's why control flow integrity would not be useful on the return edge, and we need something stateful that has actually a stateful view of the program as it is being executed, as for example a shadow stack or a safe stack. For indirect calls and jumps, attacks like co-op, counterfeit, object-oriented programming have shown that full functions can still be used as gadgets. Right? And I just mentioned this before, control flow integrity itself is stateless. So there is no dynamic control flow or data flow that is being used as part of the analysis. Each state is verified without context, and CFI is clueless about constraints between states. Right? So some academic proposals try to add some statefulness, but this usually results in quite a bit of detection and quite a bit of overhead and issues with the different targets. Right? So this is not as compatible as we would like. And any target in the target set is valid. So weak CFI implementations are trivially broken, and function reuse or arity sets usually give attacker enough flexibility, depending on the target set. Now, there's a couple of limitations, right? Attackers may bend the control flow along the valid control flow graph, run advanced data-only attacks to jump between useful blocks, and if we assume this fully precise control flow integrity without stack integrity, this is trivially broken, right? Just as a demonstration of why we need control flow integrity on the forward edge and something stronger on the backward edge. If you look at a control flow graph, you may think between a vulnerability and the call to system, the control flow graph would be this complex, dependent graph with a lot of limitations that make this extremely challenging for the attacker to achieve. Right? So you would assume that the attacker requires this complex path through the control flow graph. But interestingly, if we do not protect return instructions, there's usually a simple target that allows the attacker to shortcut from a vulnerability to, for example, one of these super powerful functions like memcopy, and then returning from memcopy, jumping into system, right? So these are like shortcuts in the control flow graph that the attacker could bend control flow through and go back and forth. Now, an interesting angle here is dispatcher functions that can be called on the stack, right? So these are frequently called, and the arguments here are under the attacker control. And if you look at memcopy, memcopy is one of these dispatcher functions that if you control the destination with setting it to the return address, for example, the memcopy itself can modify where it returns to, right? So memcopy can clobber its own stack frame and thereby redirect and hijack control flow accordingly. So far so good, right? So let's, in summary, CFI is still useful. It makes attacks much harder. It's an advanced mitigation that protects the forward edge. CFI checks, as we've just seen, are insufficient to protect the backward edge. The compiler statically infers the per call target sets during compilation and during analysis, and at runtime the set check ensures that the observed target is valid. Runtime overhead is low, usually less than 2%, and the security is pretty good, assuming that we have some form of stack integrity through shadow stacks or safe stacks. This makes attacks much harder. Can we do better than this? Well, one thing we tried is code pointer integrity, where we try to enforce the actual integrity of the code pointers. We observed that memory corruption is abundant, And strong memory safety based defenses have not been adopted primarily due to the massive amount of overhead. Weaker defenses like strong memory allocators are also ignored. Only defenses that have negligible overhead are adopted. Can we have the benefits of memory safety, but only where it matters by enforcing memory safety for a small subset of data? If you want to protect against control flow hijacking, the data we need to protect is code pointers and anything that points to code pointers, right? So code pointers must be protected at all times. Comparing this against memory safety solutions, Softbound and CETS have 116% overhead, only partial support, lots of bugs and errors. Secured has 56% overhead. AZEN, which is not a mitigation, has 73% only overhead. Right? All of these checks focus on all data. How can we protect the integrity of only code pointers? By enforcing integrity of a subset of data. So instead of protecting everything a little, we protect a little completely. So we want to have strong protection for a select subset of data. The attacker may modify any unprotected data, and we don't give any guarantees about the unprotected data. By only protecting code pointers, code pointer integrity reduces the cost of memory safety from 116% to 8.4%, and thereby deterministically protects against control flow hijacking. Now the question is, what data we should protect? And we define this as sensitive pointers. And sensitive pointers are code pointers plus any pointer that accesses sensitive pointers. So this is a work list algorithm where we continuously, iteratively scan for pointers that are pointing to sensitive pointers, and we make those pointers sensitive as well. As an over approximation, we can identify sensitive pointers through their types. So all types of sensitive pointers are sensitive. And this over approximation only affects performance because we are just protecting more pointers, right? And we've changed the memory layout from on the left-hand side, where everything is in one address space, to kind of two layers, a data plane and a control plane. In the control plane, we enforce full memory safety, while as in the data plane, we just leave the other remaining data pointers that can potentially be accessed in an unsafe way. Memory view is split into two views, the control and the data plane. Control plane contains the code pointers and transitively all related pointers. The data plane contains only data. Code pointers are left empty. The two planes must be separated and protected against each other, and thereby to ensure that the dereferences in the data plane cannot modify the control plane. So code pointer integrity protects code pointers and sensitive pointers and enforces memory safety for the select data. Code pointer integrity prohibits control flow hijacking. Unfortunately, the overhead of 6 to 8% is seen as too high for general deployment, and it requires some additional work on the compiler toolchain as well. But it's an academic proposal as a prototype on making protections more secure and going beyond the limitations of control flow integrity. Last but not least, we want to look at sandboxing. Sandboxing gives us different guarantees. So instead of having one large code area and where we have to argue security benefits across this large code area, sandboxing allows us to separate code blocks into smaller fault domains. And there's different levels of sandboxing. The kernel isolates process memory, chroot or containers isolate processes from each other, and seccomp restricts processes from interacting with the kernel. And software-based fault isolation isolates components in a process itself. Sandboxing, kernel-based sandboxing. The kernel provides the most well-known form of sandboxing. This is the process abstraction, as we've seen and are used to. Processes are sandboxed and cannot access privileged instructions directly, and only the kernel is allowed to execute privilege instructions. Right? To access resources, any process must go through a system call that elevates their privileges and then asks the kernel to handle access. The kernel uses this to enforce security, fairness, and access policies for different hardware and whatnot. The sandboxing is enabled through hardware. and especially the different privilege levels exposed by the ISA, the instruction set architecture, that allows a user space program to request services from the kernel by elevating their privileges and trapping into the kernel. This is usually a heavyweight operation and quite costly. That's why it must be used rarely. Right, and this was one of the key limitations of microkernels, where the context switching cost from user space to kernel space is one of the key limitations that impacts their performance. Containers, like Docker, for example, are a lightweight form of virtualization. They isolate a group of processes from all other processes. Here, root is restricted to a container, but not the full system. And then sandboxing is powered in software through the kernel data structures that kind of limits how the container can interact with the rest of the system through a set of namespaces and other kind of issues. SecComp is another such limitation or another such system to implement sandboxing, and it restricts the system calls and parameters that can be executed by a single process. So seccomp is a magic system call, and after calling seccomp, you're only allowed to call the system calls that are specified by the policies. For example, in its most restricted, most constrained form, you're only allowed to call the 5 system calls: read, write, close, exit, and sig return. So during the setup phase, the process will will open up all the files, all the pipes, all the information it needs, and map it into its address space. And then it calls seccomp, and after which it can only read and write from and to existing file descriptors, close file descriptors if they are no longer needed, and exit the program, along with returning from any request from the kernel. Here, the sandboxing is also powered in software through the kernel data structures, heavily limiting how the process can actually interact with the target, with the kernel. Software-based fault isolation is another sandboxing mechanism where the kernel limits where the instrumentation limits the interaction inside a single address space. So this is different from the kernel-based sandboxing, where in CFI, software-based fault isolation, the instrumentation in a single process limits how it can interact with other parts of the kernel, other parts of the program. Sorry, right? So CFI restricts code execution and data access inside a single process. The application and any kind of untrusted code, they run in the same address space, and we leverage instrumentation to ensure that transitions between different segments are verified. Right? For example, on x86, you could use segmentation and thereby have a couple of different views into the address space, or you could mask memory errors, and this is the most commonly used instrumentations. For example, with masking, you can mask the pointers before they are being used, and if you assume code integrity, then the masking will ensure that the mask is always applied and can be verified through a simple check. A challenge for variable length instruction set architectures is jumping to unaligned instructions, and here the jumps will obviously have to be aligned as well. So all the instructions have to be aligned to a certain target set, and sandboxing is allowed through this software-based instrumentation. Now, if we summarize the defense strategies, right, that we've seen, at the memory safety level, we can stop memory corruption at any point in time through safe C and C++ dialect, secured, cyclone. We can retrofit this on C and C++ through soft-bound and sets, which we'll hear about some more. And then we can rewrite in safe languages. Integrity testing is lower overhead and still focuses on the integrity of code pointers. There's different approaches out there, such as write integrity testing, code pointer integrity, which we've just seen, and data execution prevention, and write XOR execute for code, for example. Randomization is a probabilistic defense that randomizes locations, code, data, or pointer values and ensures the integrity on that end by prohibiting the attacker from learning the targets. But it's often bypassed through information leaks. At the last level, we can protect against control flow. We can protect control transfers through data flow integrity or control flow integrity, kind of limiting the usage of already corrupted code pointers. If none of these protections work, then we have a successful control flow hijack attack. These two top areas, these are hot research areas at the moment, and certainly require additional attention. How can we enforce memory safety using compiler-based extensions? There's a couple extensions currently going through the C and C++ standards that will be interesting to, for example, protect stack pointers, but also heap data. Similarly, for integrity protection, enforcing this using hardware extensions is also an interesting research area. So, summary of what we learned today. Well, first off, the deployed mitigations cannot stop all attacks. Deployed mitigations are ASLR, DEP, stack canaries, and safe exceptions, and they already make attacks quite a bit harder. But especially on the contraflow hijacking side, the attacks remain quite versatile, and attackers use contraflow hijacking to implement different forms of arbitrary code execution. To limit contraflow hijacking, we've discussed a set of advanced mitigations today, such as stack integrity, which will guard the stack, as in these are all the return instructions, returning from function call. Contraflow integrity on the forward edge restricts targets on the for indirect calls, virtual dispatch, and so on. And code pointer integrity similarly protects the forward edge and protects against contraflow hijacking by enforcing memory safety only for code pointers. And then sandboxing kind of separates different privilege domains and stops the execution against different kind of attacks.